In the first lecture, I will try to introduce the membrane and say what is the membrane and why we want to use the membrane instead of traditional methods, and what is the mechanism of separation in membranes, and we will define the usual words that use in membranes, such as what is rejection, flux, recovery, and others. The first definition is what is membrane. We usually say that a membrane is a semi-permeable physical layer. A semi-permeable physical layer. That means membranes allow some materials, some species, some molecules, or some ions can pass, and others cannot pass. Okay? And this is a definition, a simple definition that we have a barrier, and this barrier mostly is a porous layer, porous barrier. But we have non-porous membranes also. But most of the membranes is porous, and we can say that a membrane is similar to filters, but different from filters. In filters, we only separate solids from fluids. We separate particles from air. We separate particles, microorganisms from the water with filters. Okay? The fluid, the gas, the liquid pass from the filter, and the solids do not pass. But in membranes, we can separate dissolved ions, dissolved molecules in liquid that filters cannot. The difference between filter and membrane is that the membrane can separate dissolved ions, dissolved molecules from the fluids. But in filter, we have only separate particles. Therefore, the pores of the membranes should be very small than the filters. Usually, the filters have 200, 300 nanometers in pores. But most of membranes have pore size less than 100 nanometers. Okay, therefore we can say a membrane is a nanotechnology because we can produce pores in nanometric scale. This is a simple picture of the membrane. You see that the small molecules can pass and the big molecules cannot pass. But this separation, in most cases, is not complete. It's not complete. We have not complete separation of a species. We have rejection, for example, 98%. That means some molecules cannot pass, and some solvents or some ions, some molecules can pass. And therefore, the selection, the selectivity is not infinite. We have a restricted separation because the pore size of membranes usually is not uniform. We have not uniform size of the pores. When we say these membranes have, for example, 20 nanometer pore size, this reported data is average data. We maybe have 15 nanometers or 30 nanometers. Therefore, we have not the equal and similar pore size, and therefore, when we have a non-linear pore size, therefore, we have not complete separation. The second question is that why membrane separation is important, especially in recent years. Because the main reason is that low cost or low energy consumption. The membrane separation is a physical separation in most cases. We have also some chemical separation, such as liquid membranes. But in the most cases, we have a physical separation and no need to any phase separation in liquid or gas. For example, in distillation, we must boil the water for boiling and transfer from liquid phase to the gas phase for separation. And this phase change needs very high energy. But in membrane, we have not phase change. In separation, we have a liquid, for example, in reverse osmosis, with using this barrier, the water pass from the membrane and the solutes, the ions, the salts cannot pass. And we only apply pressure. And for this applying pressure, we use pump. And the pump uses energy. But the use of energy in pumping is very, very low from the boiling. And therefore, reverse osmosis now substituted with thermal processes. And the most application of RO membranes is desalination. Other reason is that flexibility in designing. The membranes needs a very low space, and we can compact the models, pressure vessels, in a very low space. We can put the membranes to the high or to the right and the left, vertical or horizontal. And we can change the designing. But in distillation, for example, we must prepare a very tall column, and we cannot fabricate the column as a vertical or horizontal. Okay? Therefore, the membrane design is flexible. In membrane separation, we usually have no dangerous waste. In membrane, we have a permeate and we have a concentrate. This concentrate is problem in membrane process, but no produce new waste, new dangerous waste, or no use dangerous and toxic chemicals. For example, in absorption column, we use amine solutions for absorption of carbon dioxide. This amine solution can lead to the weather and is dangerous. But in membrane processes, we have not dangerous additive or dangerous gases, and therefore, generally, the membrane process is environmental friendly. And we have no risk and hazards, very low risk. We usually use the pressure of 2 atmosphere, or in RO, we use 50 atmosphere pressure. And this pressure is not important. For example, in production of polyethylene from ethylene, we have a 700 atmosphere pressure. And 50 atmosphere pressure is very low in industry. And we have no risk about the destroying of the equipment and other problems. Therefore, the membrane process is an economical, environmental friendly, and low risk process. I say the advantages of the membrane processes, but we have some drawbacks and disadvantages. The main disadvantages of the membrane is fouling. Fouling means that the productivity of the membrane reduces during the time. The flux reduces or the rejection is reduced. The selectivity is reduced. In the first day, we have a high flux, and after 2 months, due to the plugging of the pores, due to the layering of a foulant layer on the membrane surface, and other reasons, the flux reduces, the selectivity reduces, and after 1 year, 2 years, based on the membrane, we must change the membrane. Or for reducing the fouling, we must wash the membranes. For example, in dairy industry, we wash every day the membranes because the protein of milks can attach to the membrane surface and causing to fouling. But in reverse osmosis membranes, we usually every 3 months we wash the membranes. Okay, related to the membrane process, the cleaning and washing is different. But cleaning and washing need to money and cost, need to the washing agent, need to the labors for these works. The second problems in membranes is low selectivity and flux. As I say, that the separation of membrane usually is not complete, and we have 90% rejection, but some processes usually, for example, distillation, usually have complete separation. And we try to increase the selectivity and the rejection of the membranes. And another problems is the high capital cost. We say that the energy consumption of membrane is low, but first capital cost is high because membranes is high technology. But during 20 years, the price of membrane is reduced. For example, 30 years ago, 8-inch RO membranes had $1,500, but now reduced to $700, half of the 30 years, because when the RO membranes is used mostly, the production increases and the cost reduces. Therefore, we have a high capital cost, but this capital cost reduces, and in the future, we have not this problem. Membrane is a separation process. We want to separate two species from together. Therefore, wherever separation is required, membrane can be used, but if it is economically viable. If we see that the membrane have economical viables, we can use the membranes. Almost in all separation process, we can use the membranes. And we have almost 20 different membrane processes, and we can separate gases, liquids, organic solvents from their purity. And therefore, you see, in most of the technology and factory, we can use the membranes for separation of some impurities from the air, from the gas, from the soil, from the water, and medicinal, breeding, agriculture, and others. Therefore, the membrane scientists first check the economical viability, and the second is fouling problem. Maybe one process can be instituted with the membrane, but the membrane will destroy during 1 week. Membrane can be separate, but have not durability, chemical durability, solvent durability, thermal durability. Check these conditions. If the membrane can be used for a long time, membrane can be used instead of a traditional process. About membrane materials, we can say that all materials can be used for the membrane fabrication. Polymeric, organic materials, inorganic or ceramic materials, metal or liquid. We have all liquid, solid, metal, non-metal, inorganic, ceramic, and polymers. The usual polymers used in fabrication of the membranes is polysulfone, polyethersulfone, cellulose acetate, regenerated polyamide, and generally, membrane can be made from all of the polymers, polyethylene, polystyrene, biopolymers, chitosan, polylactic acid, and every polymer. We can increase the stability of membranes, polymeric membranes, with cross-linking. When we have a polymer is not suitable for membrane fabrication, we can change the properties of polymers. For example, with sulfonation, with carboxylation, with amination, with cross-linking, or addition of other additives, or blending of a polymer with other polymers. Therefore, you can find in literature that every polymer have been used in membrane fabrication, but the mostly used polymers are these polymers. A good polymer should have good flexibility. The flexibility and durability of the membrane is important. Membrane is a thin layer. The thickness of membranes is about 100 micrometers, usually, and very thin. But if the polymer is brittle, we cannot apply pressure. We cannot use the brittle polymer in membrane fabrication, and we usually use amorph polymers in membrane fabrication, amorph, not crystalline. The crystalline polymers is brittle, and we cannot use, and the molecular weight of the polymers should be high. In some research, one researcher told me that I have now synthesized a novel polymer, and you can prepare a membrane. I asked him the molecular weight, and he said that the molecular weight is 5,000 grams per mole. This 5,000 is not good for membrane fabrication, and when we fabricate a membrane, we see that the membrane is brittle. And we need to high molecular weight for flexibility and chemical resistance. And the polymers in most fabrication process, need to dissolve in solvent. We must first dissolve the polymers in good solvents and next prepare the membranes. And in most cases, the synthesized polymers have not good solubility and we cannot use them. Therefore, we must change the properties of polymers to good processability and dissolving. We have ceramic membranes that usually fabricated from alumina. The ceramic membranes is expensive than polymeric membrane because the use of materials is high and the need for high temperature for fabrication. For example, when we use the alumina for fabrication of membranes, we need 1,700 centigrade temperature for 6 hours, 8 hours for sintering of these materials, and this causes the high cost. And the fouling of ceramic membranes is lower than the polymeric. The durability, chemical resistance, solvent resistance, thermal resistance of the ceramic membranes is better than polymeric membrane, but ceramic membrane is not flexible and is brittle. When we want to use with a little small touch, can be destroyed, can be brittle, and we cannot use them, but the fouling in ceramic membrane is very low. In daily industry, usually use ceramic membranes. When we have a hot stream, hot gas, hot water, we use ceramic membranes because the polymeric membranes is destroyed in high temperature. Usually the polymeric membranes used in lower 50 centigrade temperature. But ceramic membranes can be used to 100, 300 centigrades. Metal membranes mostly used for hydrogen separation that Professor Raka will speak about. But we can fabricate porous metal also. We can porous metal membranes that we can use as a microfiltration and ultrafiltration, but they are very, very expensive and used in nuclear processes for separation of some pollutants. And we have a liquid membranes that in liquid membranes, we usually have a support that the liquid is supported. And the main separation agent that we say carrier membrane is liquid phase. We have, in most cases, solid substrates, solid support. But they're only support. And the main separation layer is liquid that we will discuss next. In this slide, we define the most used words and terms in membrane process. We have a permeate. Permeate is the part of feed stream that passes from the membrane. If this is membrane, this solute is permeate. The permeate is the feed stream that passes from the membrane, and for showing the selectivity and the rejection, we usually measure the concentration of the special solute, special ion, in permeate and feed, and compare it for saying that the rejection. With the measuring of the, for example, A component in permeate, and the first concentration in the feed, we can say that how many of the molecules or ions are rejected. Reject, that means not pass from the membrane. Rejected solution and rejected ions or molecules. Therefore, we need to measure the concentration of the solutes. In the lab scale experiments, for example, in your thesis, the measurement of this concentration is problematic. Maybe we need HPLC, GC, UV spectrophotometer, and other techniques for measuring, and true measuring is important. Analytical chemistry is important in this case. When we have a wrong analysis of concentration, our rejection will be wrong. Therefore, in lab scale, we need to high technology for measuring of the concentration. For passing of the permeate from the membrane, we need driving force, a force that pulls the solids from past the membranes. We generally have 4 driving force: difference in concentration, difference in pressure, difference in temperature, and difference in electro potential. Difference in pressure, that means we must have high pressure in the feed side than the permeate side. Usually in microfiltration, ultrafiltration, nanofiltration, the permeate size is better and the pressure is 1 atmosphere. But we apply 2, 3, 4, 5 atmosphere in the feed side that is higher than the permeate side, and this delta P causing to the passing of the permeate from the membrane. Or from the delta C, we must have a difference in concentration for diffusion of the solutes from the membrane. Therefore, we have a transmembrane pressure, that means delta P. For saying how amount the permeate is past the membrane, we have flux. That flux with a unit of kilogram per meter hour or liter is the amount of the current penetrated, percolated, or passed from the membrane per unit time and per surface area of the membrane. With a high membrane surface or high time, we will have a high flux. We have also permeability. Permeability in gas separation and water separation is different. I will define permeability in gas separation, but in permeability in the water, in liquid separation, is the pressure, is the ratio of the membrane flux to applied pressure. We divide the flux to the applied pressure, and this is the permeability. Permeability is flux per delta P. This is in liquid separation. In gas separation, the definition of permeability is different, and I will speak later. Another definition is recovery. The membrane separation is a mass transfer mechanism, and we can write mass balance for the feed and permeate. when we write the mass balance, we say that the flux or flow of the feed equal to the flow of permeate and flow of concentrate. In most cases, when we test the membranes as a cross flow test, that's UF, RO, and F, some gas separations, is the cross flow test. We have a feed stream that comes to the membrane surface and divide two phases. One phase is the permeate that pass from the membrane, and the second stream is concentrate or retentate or rejected stream. We have a one entrance divided to two streams. One stream is permeate and one stream is concentrate. Related to the membrane process, the main product can be permeate or can be concentrate. For example, in reverse osmosis, our product is permeate. We want to desalinate the water and produce desalinated water. Therefore, permeate is our product. But in a UF process, in most cases, our product is concentrate. We want to separate water from a solution and concentrate it. For concentration of milk, we want to reduce the water of milk. Concentration of dye. We want to concentrate the textile dye for reuse in dyeing. Therefore, related to the membrane process, the main product can be concentrate or permeate. About the mass balance, we say that mass is not destroyed. Okay? When we have, for example, 100 kilogram feed, the sum of the permeate and concentrate should be 100 kilogram. And we can write partial mass transfer. I define the rejection that show the ability of separation. But we have a recovery. What is recovery? Recovery is meaning that how many amounts of the feed result our product. In this case, you see, we usually, the permeate is our product. The amount of our product, that means permeate, per amount of the feed. For example, we have 100 kilogram feed, and this changes to 70 kilogram of our product. Our recovery is 70%. Okay? Understand? The recovery is meaning that how many we have useful products per the first feed amount. The high recovery is good because we will have the high product. Okay? But in membrane process, we cannot reach to complete recovery. We cannot reach to complete recovery because the complete recovery means that all of the solvent should be separated from the solute. And when we have a high concentration of solutes on the membrane surface, causing to the high fouling. We can separate all of the solvents from the liquid. But when we have separate all of the solvents, a layer will be covered the membrane surface and block all the surface, and the membrane will be destroyed. Therefore, we have not complete recovery. Based on the process, we have usually 75% of recovery. Sometimes we can increase to the 90% based on the feed concentration. If the solute concentration is low, we can increase the recovery ratio. Therefore, recovery shows that how many products can be produced. For example, in the commercial modules or modules, after preparation of membrane, we change the membrane to the module form. What we say in India, module or module? Module or module? Module. Okay. In the module, we change the membranes to module. In the module, we increase the area to volume of the membranes for industrial application. This is the catalog of the commercial film tech, and you see that the recovery of a module with 1 meter length is only 50%. That means if we want to reach to, for example, 75%, we must use 5 series modules to reach the 75 recovery. Therefore, with 1 module, we can only reach to 10 or 15 recovery. And for increasing of the recovery, we must use the series modules in a pressure vessel. Therefore, in industrial pressure vessels, we usually use 4, 5, or 6 modules in series that the concentrate of 1 module go to the second go third, and parallel goes. In industrial modules, usually say the flux with GPD or GFD, that is gallon per foot square day or gallon per day. GPD is flow, GFD is flux. GPD is flow, no area, you see no area, but GFD is flux that have area of the membrane used. From a theoretical view, the flux in the filtration membranes, that driving force is delta P, can define as this mathematic. The delta P is the top, is the above, and the viscosity and the resistance in the bottom. You see that when we increase the pressure, the flux, the permeability will be increased. But with increase of viscosity, the flux will be reduced, and we have a membrane resistance. Resistance that is all of the resistance that cause to reduce the passing of a solute from a membrane. A membrane is mass transfer and wants from one location to another location. All of resistance that there is in this pass road can name as the resistance. For example, membrane pore size. With reducing of the membrane pore size, the passing is hard. is problematic, and with the reducing of pore size, the resistance increases. Porosity. Porosity is the free space in the membrane body or in the membrane surface. With the increase of porosity, resistance reduces. High porosity, high flux. Affinity in some mechanisms, in solution diffusion, in ion exchange membranes, we have shown functional groups can interact, can attach, can affinity to a molecules or ions and give these molecules and pass and diffuse from the membrane body. This hydrophilicity, this interaction is important. High affinity, high hydrophilicity can cause the high flux. Surface charge, in some cases, the surface charge is very important in separation, in nanofiltration membrane, in fouling phenomena, the surface charge is very important. Membrane thickness, higher thickness, lower flux, and others. In lab, we usually have a membrane with specific surface area. We cut a circular membrane in 5 or 6 diameter and measure the flow. We use a vessel and collect the passed water and weight or measure the volume and in the specific time. With the measuring of the volume in time and we having the area, we can calculate the flux. Okay, very simple. And we have now the applied pressure. We know the viscosity of our solution, usually water, and we can calculate the resistance. With obtaining the membrane flux in the lab, we now apply pressure, we know the viscosity of solution, we can calculate the membrane resistance. We know that resistance of ultrafiltration membrane is higher than microfiltration because have low molecular pore size, low pore size. Usually for testing of the membranes in lab or industrial scale, we have two regimes of the flows. We have a dead-end filtration or we have cross-flow filtration. In cross-flow, we have a cross movement of the fluid related to the membrane surface. Here, the permeate side, but the feed is have a 90 degree with the permeate pass and the flow pass. Therefore, we have a cross. Okay? We say cross flow because the feed and permeate stream have a cross section. But in the dead end, the feed flow and the filtrate or permeate flow is parallel. In industrial case, we want mostly use the cross flow because the cross flow push all of the substance and foreign agent from the surface and sweep the membrane surface and reduce the concentration polarization and reduce the fouling. But in the dead-end method, we have a high concentration we say this is the cake layer or gel layer. This cake layer and the gel layer increase membrane resistance because act as a barrier layer, that increase the membrane thickness. First, the solute should pass from this thick layer and the next receive to the main membrane. But in the cross flow, the thickness of the concentration layer is low and the fouling is lower. Therefore, in cross flow, the fouling is lower than the dead end method. In industry, in most cases, we use the cross flow for reducing of the fouling, but in some gas separation, we have a dead end, or in a syringe filter that's used in medicals for separating of some things from the blood. We use the microfiltration membrane as a dead end method. As I said, that the membrane process is separation process, and we have a mass transfer in membrane also, but we have a difference, and that in this is video, but not today. In the membrane process, we have a vector for passing in this random mass transfer, but in the membrane, we have transfer from left to right, and we have a vector, and for producing this vector, we need driving force. That's delta P, delta E, delta C, close to the passing in a line and in a vector form. We have a diffusion. We have a diffusion mechanism in membranes, and this diffusion mechanism can be increased with external force. With external force, we increase the diffusion coefficient in fixed laws. Fixed laws, we have DRB. In D, with external force as a pressure, we increase this constant for passing from the membrane. Generally, separation processes has in single phase or between two phase. As you know in mass balance lesson, you know that in single phase we separate from liquid to liquid. Or in the between two phase, we have two different phase: gas liquid, gas solid, liquid liquid, or liquid solid. Most of these processes is direct contact or direct contact. That means that the liquid phase direct contact with gas phase. But in the membrane, we have indirect contact. That means we have a barrier and no contact between the two phases. But we have a mass transfer between two phases. All of this process have a mass transfer, okay? One solute, one species, separate, for example, from liquid to liquid. Liquid extraction, we have a water phase and liquid phase. One samples adsorb to the organic phase, and this separate from water phase. But in membrane, we have a indirect contact, and this causes that we have a pure products relatively. We have a mathematical equations for for discussion about the membrane flux and permeability. As a general equations, we have a delta X per L. L is the thickness of the membrane or the road that's from A to B, the mass should be transferred. Okay? We have a 2 point A to B. In mass transfer, the distance is important. This distance is L. In the membrane science, this distance is membrane thickness. Therefore, if we fabricate the thinner membrane, the flux will be increased. Therefore, we must prepare 100 micrometer membranes because the flux is very important in membrane separation. And delta X is the driving agent. Delta P, delta E, delta C, delta T, that generally is named chemical potential difference. Delta X, chemical potential difference for passing of a particle, a molecule, from point A to point B need a chemical potential difference. And this chemical potential difference can be pressure, temperature, concentration, or electrical potential. Usually, we have a passive transport. Passive transport means that we go from high potential to low potential. All of molecules want to reduce their energy, their potential, and therefore in passive transport, we go from high temperature to low temperature, high pressure to low pressure, high concentration to, but this is a passive transport. But we have a non-passive transport. That means active transport. Active transport is the reverse of passive transport. In the passive, we go from high to low, but in the active, we can go from the low to the high. This transport in membrane is named carrier membrane or facilitated membrane, facilitated transport. In this facilitated transport or carrier mediated transport, usually used in liquid membranes, we have a special agent, such as a complex, that this complex ligand, complex molecule, can connect to the, for example, heavy metal, and extract the heavy metal from low concentration to high concentration. This is the fit side. This is the permeate side. In active transfer, we have a low concentration to high concentration, but for this transform, we usually need a carrier that you see, which show with C. This carrier come, interact with A, and go to the permeate side and release. For this attachment and release, we need a change in a response. For example, here we have a pH 8. Here in the permeate side, we have a pH 4. with change of the pH, this carrier can complex with metal, and with reducing the pH can release. Okay, this membrane is also named as intelligent membrane or responsive membrane. With the change of temperature, with change of the pH, or with change of the concentration, with change of electricity, they can absorb or dissolve. And intelligent or smart membranes. So this gradient also say this also problem with this. Based on the driving force, we can different membranes for pressure gradients. We have a microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. In the microfiltration, you see we can separate big particles. We can separate bacteria, particles, and others not good see. This here is better. Red blood, but in UF we can reduce, we can separate. In UF we can separate virus, gelatin, and generally macromolecules. In nanofiltration, we can separate the synthetic dyes. Molecular weight is 1,000 gram per mole. Heavy metals can separate calcium 2 plus from sodium 1 plus, sulfate 2 minus from chlor 1 minus. But RO separate all of the solids. Okay? When we use the RO can separate all of these ions and molecules. One question is why we not used RO for separation of this. When we can use one process for separation of all these molecules, why we use MF? Why we use UF? We can use RO for separating of all of them. But with going from right to left, microfiltration, UF, NF, and RO, we need to high pressure. And high pressure means high energy. Therefore, the energy consumption of RO is very, very high than MF. In MF, we use 1 bar pressure, but in reverse osmosis, we use 30 bar, and therefore need to high energy. Also, the flux of MF is very, very high than RO. Therefore, when we can separate a solutes with lower pressure, lower energy, and high flux, we no need to use the RO. Therefore, RO is used for desalination and is the high price technology. So, based on the concentration gradients, we have a dialysis, evaporation, gas separation, and liquid membrane processes. We have 22 membrane processes. I can present in this slide. For electric gradients, we have electrodialysis membranes or electromembranes that I will discuss after these processes. And for temperature gradients, we have a membrane distillation. That in membrane distillation, the vapor passes from the membrane, not liquid. And with using of membrane distillation, we reduce the energy of distillation process and use for very, very high concentration. Usually MD used for concentrated solution of reverse osmosis. About morphology and structure of membranes, the membranes can be porous or non-porous. Membranes can be porous or non-porous. Membranes can be symmetric or asymmetric. Can be isotropic or anisotropic. Symmetric equal to isotropic, asymmetric equal to the anisotropic. Symmetric in the membrane is not right and left. Symmetric is top and bottom. Very small. You see in this, the right and the left is similar. But when the membrane is anisotropic, means that the top and the bottom is different. You see that here in the top layer, we have small pores, and in the bottom layer, we have big pores. Therefore, this is a asymmetric membrane. Or in this case, we have a non-porous layer coated in a porous support. Therefore, the top and bottom is different. In this type, that we have a thin layer on the support, the membrane is called thin film composite. Thin film composite, TFC membranes. In TFC membranes, we have a very thin layer, non-porous layer on the support and used in reverse osmosis, nanofiltration, gas separation. And these membranes usually have very high flux rather than this dense membrane. In this scanning electron microscopy, you see the real SEM image. So the right one is the symmetric, the top and bottom is similar, and is the porous, and have a spongy structure. We say that the structure of membrane is spongy. In the left, we have a finger-like structure, similar to the finger, and we have a finger-like and have a asymmetric. Asymmetric, that means the top layer pores is smaller than the bottom layer. When we zoom, that see that this pores is smaller than the bottom layer, and this membrane is also named as Loeb-Sorirazan membranes. Huh? Okay, okay.
So that they can reconnect the.
Okay, perfect. Thanks. One hour is low. My slide is not comprehensible. One. I continue 30 minutes. Yes, finish. I send rapid speed. I will come. So if you continue, then I will start my session after. No, you. Afternoon, you present your lecture, and if my presentation is not complete. In the tutorial, I speak about this and continue the lecture. We have we can. Open.
Being recorded, no? Is it okay now? Please finish up whatever you take need time to complete your session. After that, we'll plan.
Okay. Okay.
It's going good.
Okay. Is there a question? You can ask your question about I discussed up to now.
If the participants have any questions or would like to interact with the presentation, please feel free to talk. Because we have okay, now we're okay, fine.
Okay. As I discussed, the membranes can be porous or non-porous, and the porosity can be different, such as finger-like, spongy, macrovoids, mix-up spongy finger-like, and very different structure. But usual structure is the membrane is non-porous, spongy porous, and finger-like porous. But we have other structure also. Based on this structure, we can different separation mechanisms. In the porous membranes, we have usually size exclusion mechanism. In size exclusion, our molecular sieving mechanism, we have a porosity that the small molecules can pass, and the big molecules cannot pass or low pass. Therefore, in porous membrane, the main mechanism in one separation, maybe we have three mechanisms together. For example, size exclusion mechanism, adsorption mechanism, and charge retention mechanism. But generally, in porous membranes, we have a size exclusion mechanism that called also molecular sieve or IL sieve mechanism. In non-porous membranes, we have no density, no porosity. We have a dense membrane. We have no porosity and we have a dense membrane. That means we have no pores. And in this case, we have solution diffusion mechanism. We have two steps. One molecules should be first adsorbed on the membrane surface. For this adsorption, need affinity, need functional groups. for interact the molecules from the membrane functional groups, and after adsorption, in the second step, the molecules should be diffused across the membranes. The flux of the solution diffusion is very low, and the flux of the porous membranes is high. In the second mechanism, as I say, that active transfer, we have a carrier, that this carrier only reacts with black species, and after passing from, release from the permeate size. Therefore, we have generally three important mechanisms in the membranes: that size exclusion, solution diffusion, affinity, and in some cases, we have a adsorption mechanism. Similar. Okay. In this slides, we show that the also adsorption mechanism. The polymeric membranes can have the adsorption properties and can separate some molecules, some ions, with adsorption capacity. But adsorption capacity can be freed after the certain time, and this membrane is usually used for low concentration of the feed or for low times. And usually adsorption membranes is used for one times and used in, for example, silic filters for separation of one special molecules from the liquid. We can also have electrostatic repulsion that used in the nanofiltration membranes. When we have, for example, a negative charge on the membrane surface, this negative charge can reject the negative solutes. We have a positive and negative solutes. Positive solutes adsorbed by the negative charge and pass from the membrane, but the negative ions or molecules reject. This mechanism is called Donan mechanism. In Donan mechanism, we see that the anions most rejected than cations. There are different equations for discussion about the mass transfer in the membranes. For example, Hagen-Poisson, that you see this equation is similar to the mass transfer equation. In the mass transfer equation, we write that G is delta X per R. We see that for passing of one species from the membrane, we need the driving force, and we have a resistance that's against the passing and have resistance to pass. In these equations, for example, Hagen-Poisson's, the R is defined and divided to the influencing parameters. Delta X is delta P, and R is equal to this ones. Delta X is the thickness of membrane. Higher thickness, lower flux. Viscosity, higher viscosity, lower flux. The pore size with score that shows that the pore size is very important than others. With increasing of pore size, flux increases, and epsilon is the porosity, surface porosity. With increasing of porosity, the flux increases. We have a constant here that's called as tortuosity. Tortuosity. In this Hagen-Poisson, assume that all of membrane is cylindrical. But in actual, membrane's structure is different. This is cylindrical. If the membranes have cylindrical pores, the top our tortuosity will be 1. If we have finger-like structure, the tortuosity is 1.5. And if we have a spongy structure, our ceramic membranes, we usually use this amount in equation. The second problem is the use of overall porosity or surface porosity in Hagen-Poisson equation. In Hagen-Poisson, we must use surface porosity. Overall porosity is influenced in the flux, but the important parameter is surface porosity. In this schematic, you see 3 membranes, different membranes, that these membranes have small pores, medium pores, and big pores. Okay? But 3 membranes have equal porosity. I want to say that surface porosity is different from pore size. Maybe pore size is big, but porosity is small. We cannot correlate the pore size to the porosity. Many researchers say that with increase of pore size, porosity increases. It is not true. You see in this schematic, both have equal porosity. Porosity, that means the area of pores to all areas of the membrane. And in the 3 images, we have an equal porosity, but the pore is different. Another aspect is pore size distribution. Pore size different from pore size distribution. Pore size distribution, it means that how the pore size is similar together. When we have a similar pore size, it is very good from selectivity. And these membranes have a sharp separation. If we can fabricate this membrane, is very good, very interesting. If we have fabricate this membrane, we can publish in journals with impact 30, because very important, we have a unique pore size that is isoporous. But if we can prepare a narrow membrane, also is good. But usually, we prepare this membrane. That we have a very big pores and very low pores. Therefore, when we have a different pore size, the rejection will be reduced, and the selectivity will be reduced, and the fouling increases. When we have a bigger pore size, in the neighbor of the small pore size, this pore size can be filled with the foulant and block the pores. When the pores is blocked, we cannot recover the pores in the cleaning or washing, and the membrane will be destroyed very rapid time. Therefore, in the view of the following, for reducing of the membrane fouling, it is better we have narrow or isoporous membrane. The right is better one, acceptable, but this bad membranes. Okay? This is another equation used in ceramic membranes mostly. And as you see, similar to Hagen-Basel, we have a delta P thickness, porosity, and others. I pass. We have a MF, UF, NF, RO. We say this membrane is filtration membrane. Filtration membrane that you see the pore size of the MF is bigger than UF, UF is bigger than NF. And in RO, we say we have not pores, or if we have, it is very, very small in angstrom scale, and we cannot see. Okay? Therefore, RO, not pores, or have very, very small pores. With reducing of the pores, we need a high pressure for transferring of the solutes from the membrane. MF membranes separate bacteria, parasite, particles, but cannot separate the viruses. High molecular substance, these molecules separate from the UF, and NF can separate the multi-charged ions. Mid-sized organic substance such as dyes, and RO completely separate, but most used for separation of ions, heavy metals, and salts. In application of the membrane, we have two types of pressure: direct pressure and vacuum pressure. Most of membranes use the vacuum pressure, and for applying of a pressure, we use pressure vessels. This is not membranes. This is the pressure vessels that membrane modules located inside of this pressure vessel, and this pressure vessel is used for applying a pressure. And we can apply higher pressure. But in vacuum pressure that we submerge, immerse the membranes in the water, we apply vacuum pressure with suction pumps, and mostly, and the highest pressure that we can apply in vacuum is 1 atmosphere. We can only produce 1 atmosphere vacuum, and therefore this method, vacuum, is used MF, UF, and pervaporation membranes for separation, because in this process we need lower pressure. Other methods usually used and is the famous in the membrane is reverse osmosis. As you know, we have a direct osmosis. In direct osmosis, the pure water adsorbs to the saline water or sugar water. But in reverse osmosis, we want to separate water from saline water, not pure water go to the saline water. Therefore, we must apply pressure. This pressure should be overcome to the osmotic pressure. When we have a high concentration of the salts, the osmotic pressure increases. The osmotic pressure of the seawater is higher than the well water, groundwater. High salt, high osmotic pressure. Therefore, we must apply pressure first for overcome to osmotic pressure, and second for passing of the membranes from reverse osmosis. The mechanism of the separation in reverse osmosis is solution diffusion, and I discussed that in solution diffusion, the solvent, mostly water, adsorb on polyimide polymer. Polyamide polymer is hydrophilic polymer, and pass and diffuse from the polyimide and goes to the permeate side. The diffusion process, solution diffusion process, is very slow process, and therefore we must prepare a thin layer. We have a top layer, you see, this is the structure of the RO membranes. We have a non-woven baking or non-woven fabric for increasing of the membrane durability, membrane strength. We have a polysulfone support layer for supporting this polyimide thin film layer. You see the thickness of the active layer and selective layer is very low, nanometric layer. If we prepare this layer, instead of this amount, we increase, for example, 1,500 nanometers, 10 times increase the thickness, we will have no any permeate because the diffusion is very, very low, and therefore we must prepare a very thin layer. But thin layer has not good stability, can be easily tear, and therefore we prepare this layer on a support for increasing of the stability and durability. The main layer, this active layer, selective layer, and these two layers is supporting and increasing the membrane stability. You see, for fabrication of the RO membrane, we use interfacial polymerization method, and we polymerization. You see that we have a very angstrom scale pores, and in these pores, the water only can pass, and the hydrated salts such as sodium and chloride cannot pass because one sodium hydrated with 6 water and have a big size and cannot pass. Another separation mechanism, as I discussed before, Donan exclusion. In a Donan exclusion, the charge of the membrane is important. When we have a negative charge, on the membrane surface, you see that the sulfate ions with 2- charge more rejected. After that, sodium chloride, and after that, calcium chloride. We have a negative charge on the membrane surface. The sulfate has 2- charge. 2- charge. Therefore, the membrane with the negative charge more reject the sulfate. Okay? When we compare these two, NaCl with Na2SO4, the sodium is similar, but sulfate have more rejection from color because color have 1 minus, okay? Therefore, the phosphate with a 3 minus will be more rejected from sulfate. But when we compare the chloride, color is similar, but sodium and calcium. Calcium have 2 plus, okay? You see that the color is similar, but change of the sodium to calcium, the rejection is reduced. Why? Because this calcium can adsorb on the membrane surface and neutralize the negative charge. Positive charge can neutralize the negative charge, therefore reduce the negative charge of membrane, and the selectivity is reduced. In the positively charged membrane, the trend is reverse. In positively charged membrane, the calcium 2 plus more rejected, sodium is moderate, and sulfate is lower. Therefore, in lab, if you have nanofiltration membrane, with test of these results, you can find that this membrane have negative charge or positive charge very easily. But for measurement of the membrane sulfate charge, we usually zeta potential device that. But this simple example can go that our membrane is positive or negative. Nanofiltration membrane have 2 types. One type mostly reject with Donan exclusion and have these trends, but some nanofiltrations membranes have a low charge or no charge, and this low charge no influence in the rejection. And in this case, the rejection you see in the previous slide, calcium is bottom of this NaCl. In this case, the diffusion rate is important, and if the molecule hydrated size of the molecule is low, the rejection will be low. We have metal. I speak about the mechanism of separation. In the metallic membranes that used for hydrogen separation, if we have a very thin metal layer prepared from palladium, nickel, cobalt, this only hydrogen membrane. In metallic membranes, non-porous metallic membranes, only hydrogen can pass because hydrogen is very small and highest diffusion coefficient. In this mechanism, hydrogen can go to the membrane surface and dissociate it to the hydrogen atoms. Hydrogen atoms pass the membranes, and the permeate size, again, hydrogen atoms connect together and produce hydrogen molecules. This take only in the surface of these metals, and this membrane is expensive, but mostly used in petrochemical processes, for example, in Haber process, for fabrication of ammonia, the methane in petrochemical process, methane changes to the carbon monoxide and hydrogen should be separated from monoxide to production of ammonia. This membrane is mostly used in this industry and have very extraordinary selective because only hydrogen gas can pass from these membranes. And as the final slides, we have ion exchange membranes. In the ion exchange membranes, we want to pass cation from cation exchange membrane and anion not pass. And for example, in this slide, for passing of the positive ions, we need two negative functional groups on the membrane structure. We have many polymeric chains. We have many polymeric chains with the functional groups of this negative charge can be sulfonic acid, can be carboxylic acid. This carboxylic and sulfonic acid can be adsorbed proton, can be calcium, can be magnesium, and we have a hopping mechanism. In ion exchange, we have a hopping mechanism that we have many membrane chains together, complicated, and have the noise and the moving. And in this moving, one functional group can contact to another. This contact to another and transfer one cation from this functional group to another. And we have a hopping mechanism to separate. For this driving force, for this movement from left to right, we need a driving force. And this driving force is electrical charge. In these membranes, we have electrodes. If we want to cation pass from the membrane, we must have a negative induction of electrical field to adsorb, to force the positive charge go to the negative electron. The driving force is electrical charge, and the mechanism is the hopping between the functional groups of this. This hop to this hop to this, to this, to this, and go to the electrode side. Thank you for your attention. I try to introduce the general science of the membranes in this lecture. And in other lectures, we focus mostly and we speak mostly, for example, in ion exchange mechanism and application and other information.
You, Professor, for the lecture, so I now request the audience to ask any questions what you have. So if the audience have any question, please feel free to register.
Thank you. It was such a wonderful and very informative talk, and I think most of the beginners also must have had a very good introduction on the topic. I just had a query, like the surface potential based or the donor and exclusion part that you have explained, that is valid for both ultrafiltration as well as nanofiltration, right? Or it is only for the ultrafiltration membranes?
About the donor exclusion, we can manage the charge of the membranes with selecting of the polymers and functionality. Most of the polymers have negative charge, and this charge also related to the pH. With change of the pH, the charge is changed. Usually the wastewater pH between the 6 and 8, And when we say that negative charge or positive charge, we tell in this range. For positively charged, we usually use amine groups. With addition of amine groups, we can use positive charge. And with negative charge, with hydroxyl, carboxylic, or natural carbonyl groups, OH groups can have a very low negative charge. This charge, in most cases, can influence the rejection, but I say that we have not only this mechanism. In the separation, we have a mix of the separation. For example, we have a more big pore size and we have a more negative charge. We cannot separate these cells. First, the pore size should be reduced to 3 nanometers, 4 nanometers, and next the pore size will be, the charge will be influenced in the separation.
Like we are currently separating lithium, so we are using ultra 4 only.
Yes.
Shift to sulfate.
Yes.
So this
Now, separation of lithium from magnesium is very important for production of batteries. And the lithium rejection is lower than the sodium because lithium is smaller. For increase of lithium, we must use the non-porous membranes, usually, TFC membranes. And the nanofiltration rejection is not suitable for lithium. In recent studies, usually use positively charged membranes for separation of lithium because the counter-ions in lithium is mostly carbonate. And carbonate is better rejection with positive membrane. Therefore, if we want to use the nanofiltration for separation of lithium, it is better we increase positive charge for increase of the salt of the counter-ions, not lithium.
thank you. Thanks.
So let us maybe please join me in thanking Professor for this secondary presentation. And so I asked the participants whether they want to continue with the second lecture or should we go for lunch first and then continue the second lecture. Most of the participants were opted for second option. So with that view in mind, let us proceed for the lunch and then we will gather at this point at sharply at 2 p.m. So the second lecture, so is it okay if I continue with the second lecture or should we want to continue with the lecture?
No important for me, as you say.
Okay. So then I will continue. I will start at 2 p.m. and then we will session with Professor Radhakrishnan will continue. So let us proceed to the last at 3:12. Okay, at 2 p.m. we shall be joining. Thank you.
Thank you. After lunch.